Assalamualaikum. In the last lecture, we learned how to sketch a root locus for a given system. In today's lecture, we shall study a few more techniques that can be utilized to further refine the sketched root locus. To understand it, let's again talk about the system that we considered in the last lecture. The system is given by So here is a system. For this particular system, to sketch the root locus, first we locate the open loop poles and zeros. So there is a pole of this system at s equal to 0. This is complex plane with real axis and imaginary axis. Another pole is at s equal to -1. The third pole at s equal to -2. And there is a 0 at s equal to -3 and another pole at s equal to -4. To sketch the root locus, next we apply the real axis rule. This is part of the root locus because to the right of all these points there are odd number of poles and zeros. This is also part of root locus, and furthermore this is also part of root locus. Now we know that root locus starts from poles and ends at zeros. So this root locus, part of root locus which has started from this pole, will end at this 0, and the root locus which started from these poles will reach to infinity, and it will follow some asymptotic lines to reach to infinity. So these asymptotic lines can also be drawn. In the last lecture we determined the center of asymptotic lines, that was at s equal to -4/3, and there were 3 asymptotic lines, one with angle of 60 degree, another one with an angle of -60 degree, and the third one with an angle of 180 degrees. So this one, root locus starting from this pole, is already following this asymptotic line to reach the 0 which is at infinity. For this the root locus will emerge from these poles and will reach the zeros at infinity, and it will follow these asymptotic lines in reaching to the infinity. So here is a rough sketch of root locus. So this complete root locus, which here starts from this pole, follows this path to reach at infinity. The root locus starting from this pole reaches the infinity, reaches this 0, finite 0. Root locus starting from this pole reaches the infinity. Here, this point, what is this point? We have not exactly determined this point up to this discussion, and this point is called breakaway point. Breakaway point is the point on the real axis at which the root locus leaves the real axis. So how to determine this this point? We can see that on the real axis, this is the point at which gain is maximum. These two points correspond to closed loop poles for k equal to 0. As we increase gain k, gain k, the closed loop poles move along this path, along this root locus, and so this is the point on the real axis. This is important. This is the point on the real axis for which the gain is maximum. So how to determine the maximum? You already know the derivative can be utilized to determine the maximum. So therefore, we shall take the derivative to determine the point which corresponds to maximum gain. Let's talk about the general systems. So a general system is given by this block diagram. The equation which describes this, here is also gain k. The equation which describes the root locus is given by 1 plus k g of s h of s. This is the equation of the root locus, that is any point in the s-plane which satisfies this equation will lie on the root locus. We can simply rearrange this equation to write it in this way. Bring 1 to the right hand side and then divide the whole expression by g of s into h of s. So we have minus 1 over g of s h of s. So this k is function of s, so let's write it as function of s. On the real axis, in this real axis, s is equal to sigma, so k of sigma is minus 1 over g of sigma h of sigma. So this equation describes the part of root locus on the real axis. We have substituted s equal to sigma, so that corresponds to part of the root locus on the real axis. So on the real axis, what is the point at which gain is maximum? Gain is maximum at this point, and you know that if we take the derivative of this gain with respect to sigma and substitute it equal to 0, it will give some points which will correspond to maximum gain. So that is the strategy to determine this gain corresponding to this point. Let's elaborate it with the help of some example. So we have this system. For this system we can sketch the root locus. A rough sketch is given by this graph. We have one pole at s equal to minus 1, another pole at s equal to minus 2, and there is a 0 at s equal to plus 3. So let's move it a little bit towards left. One pole at s equal to minus 1, another pole at s equal to minus 2. There is a 0 at s equal to plus 3, so here 0, and another 0 at s equal to plus 5, so 4 and 5. So by applying the real axis rule, this is part of root locus and this is also part of root locus. And we know that root locus will start from the poles and will end at zeros. So here is a rough sketch. The root locus will leave this real axis and then follow some path. This is a rough sketch. Exact path we are not interested in many cases. So we'll enter into this point and then approach the zeros. So this root locus is symmetrical about horizontal axis. So whatever is the graph over here, the same is over here. So root locus started from poles and ended at zeros. So we want to determine this point precisely, this point, breakaway point. For that purpose, we have learned this strategy. We determine k, which is equal to minus 1 over g of s into h of s, which in this case is minus 1 over s plus 1, s plus 2 over s minus 3 into s minus 5. And then for the real part of the root locus, part of the root locus which lies on the real axis, we have k of sigma obtained by simply replacing s with sigma, and then we multiply it. We have sigma square plus 1s plus 2s 3s, and then s replaced with sigma, 3 sigma plus 2 and with a negative sign over here, and here we have sigma square minus 3 sigma minus 5 sigma is minus 8 sigma plus 15. We take the derivative of k with respect to sigma, that comes out to be equal to the square of the denominator term, and then this term multiplied by sigma square minus 8 sigma plus 15 multiplied by derivative of the numerator, which is minus 2 sigma plus 3, and then minus, and this minus plus the derivative of this thing, sigma square plus 3 sigma plus 2 multiplied by 2 sigma minus 8. And to find the maximum point, we substitute it equal to 0, which after simplification reduces into this form: 11 sigma square 11 sigma square minus 26 sigma minus 61, which is equal to 0. So this is equal to, this gives you sigma equal to minus 1.45, and the second root is sigma equal to 3.82. So we have found the two roots, so we can just determine this point by observation. So this is minus 1.45, this point is minus 1, so, and this is minus 2, this point is minus 1.45, not at the exact center of this point, it is slightly towards this pole. So we actually, if we want to determine which point among these two roots is the maximum and which one is the not, then we have to take the second derivative to determine the maximum point. However, we can just determine it by observation. This point lies somewhere else. This is point in which we are interested. So what is this point? If we look at this part of the root locus, among all these points on this real part, which point corresponds to minimum gain? What is gain corresponding to the closed loop poles at this location? For gain equal to infinity, closed loop poles will approach the zeros. For these points corresponds to gain less than infinity and even smaller. So this is, among all these points, this point is the one which corresponds to minimum gain. So actually this second root gives you this point which corresponds to minimum gain among all these points. So this is 3.82, and this point is called break-in point. So to summarize, to determine breakaway points and break-in points, we write k as a function of sigma, take its derivative, and find the roots. Among these roots, which point corresponds to breakaway point and which point corresponds to break-in point, that can be determined just by observation. Next, coming back to our previous example, for the example system given by this transfer function kg of s h of s, that was discussed in the last lecture, given by k s plus 3 over. So this was the example which was considered in the last lecture. Now we have learned how to find this breakaway point. We shall write this as a function of sigma and take its derivative, and that will give us this breakaway point. Now how to determine these points? Over here in this graph, this graph was a very rough sketch. If we can further refine it by precisely determining these points. So how we can determine these points? So there are different strategies which can be utilized to determine these points. For example, one strategy is, at this point, real part is equal to 0. Real part of the closed loop transfer function is equal to 0. And then from that we get one equation and can find that point. In other approach, we can use Routh's stability criterion. We know that if we further increase the gain from this point, the system will become unstable. So we want to determine that critical value of k for which this system will become critically stable, and that point will correspond to these points. So we can apply Routh's criterion to determine these points. Let's elaborate it with the help of example. So it is basically the same example over here. Since these are the points on this loop locus are basically the closed loop poles, as we already know. So first we need to determine the closed loop transfer function T of S, which is equal to the forward transfer function over, in this case, H of S was equal to 1. So closed loop transfer function is the forward transfer function, which is k g of S over 1 plus k g of S into H of S. We are interested in the denominator polynomial because the roots of the denominator polynomial are the closed loop poles. So what is this thing? This is given by, if I substitute it over here, then this denominator will be multiplied over here and something in the numerator. And we want to determine this gain which corresponds to this point. If we rewrite it, this is given by k s plus 3 over, after multiplication and simplification, s power 4 plus. So after multiplication we get this expression. Now we can easily apply Routh's criterion, construct the table. Coefficients over here, 1, and the remaining coefficients. Here the entry over here is this multiplied by this minus this divided by 7. So 98 minus 8 minus k whole divided by 7. What is entry over here? This is this multiplied by this minus 1 multiplied by 0 divided by 7, that is 3k. Entry over here, this multiplied by this minus 21k divided by whole of this thing, which is actually for obtaining this entry over here, this entire row was multiplied by 7 to simplify the things. So this was 90 minus k and this became 21k, and then we have this thing over here. And then what is entry in the last row? So this thing multiplied by this minus 90 minus k multiplied by 0 whole divided by this one, that is 21k. So what is the value of k that makes the system critically stable? So that can be determined from this expression. So for critical stability, this thing should be equal to 0. That is, for no sign change, this thing should be equal to 0, which gives you, if this is less than 0, that will correspond to all these points. So exactly equal to 0 corresponds to this point where there is at the verge of stability. This gives you two numerical values, that is 9.65 and another numerical value which is basically negative. So we are only interested in the positive gains. So this point over here corresponds to a gain of 9.65. So how to, this this is the gain corresponding to this point. Where is this point actually? What is value of that s? We know that if an entire row is equal to 0 in Routh's table, we can construct a polynomial from the row above the 0 row. So let's construct that polynomial from this row. 90 minus k s square plus 21k is equal to 0. This polynomial, which is constructed from the row above the 0 row, is basically a factor of the original polynomial. So after substituting the numerical value of k, we have 80.35 s squared plus 202.7, which is equal to 0, and that gives a s equal to plus minus 0. So this point is equal to j 1.59 and this point is minus j 1.59. So how to determine these points? We can apply Routh's criterion to determine this point, and remember that all these points are the closed loop poles. Therefore we have to first construct or first to obtain the closed loop transfer function before we apply the Routh's criterion. Next we talk about another important thing which can be utilized to improve the Routh locus, and that is called angle of arrival and angle of departure. To clarify this thing, let's take this transfer function kg of s h of s, which is or rather k into g of s with h of s equal to unity, that is given by for this particular system g of s, k into g of s, given by this expression, h of s is unity. We sketch the Routh locus. For that purpose we locate open loop poles and zeros. One pole is at s equal to 0, other two poles are the roots of this quadratic polynomial, which are at this location. Minus 3 plus j4 and so Routh locus, apply the real axis rule. This is part of Routh locus. So Routh locus, which starts from poles, will end at zeros. Here there are 3 finite poles and no finite zero, so therefore there will be 3 asymptotic lines. Center of those asymptotic lines can be easily determined, and also the angle of all these asymptotic lines can also be determined. So we know that center of the asymptotic lines, the Routh locus which will start from these poles will follow the asymptotic lines. We have already discussed it, how to find those asymptotic lines. So these are the asymptotic lines. Routh locus, which started from this pole, became parallel to this third asymptotic line. Routh locus will started from these two poles will become parallel to these two asymptotic lines. So let's sketch a very rough sketch of the Routh locus is this one, and Routh locus starting from here became parallel to this one. These points can be precisely determined by applying Routh's stability criterion. Now the question is, if I sketch Routh locus in this way and another person sketches Routh locus in this way, so which one is more accurate? So this angle which Routh locus follows, this angle is called angle of departure. Angle of departure can be determined by this relation. So this angle can be determined by this relation called angle of departure, 180 degrees minus sum of angles which other vectors form. For example, here we have this vector from this pole to this pole, and another vector from this pole to this pole. What is angle of this vector? Angle of this vector is 90 degree, it is upright. So for this particular problem, this angle is 180 degrees minus this angle 90 degrees, and this angle can be determined. What is this angle? This angle is, tangent of this angle is 4 by 3. This length is 3, this length is 4. So tangent of 4 by 3. Tangent of this angle is tangent inverse of 4 by 3. Tangent of this angle is 4 by 3. So this angle is so what is this angle from here to here? Angle of this vector, that is equal to 180 degrees minus this angle. So 180 degrees minus tangent inverse of 4 by 3. So we can compute this angle, and that angle is equal to, let me calculate it with my calculator. So this comes out to be approximately 53 degrees, and therefore this 180 cancelled with 180, so minus 90 minus minus and minus plus 53 degrees. So what do we get is minus 37 degrees. That is, this angle is minus 37 degrees. Therefore, the more precise root locus will look like this one. It should follow minus 37 degrees angle. So it then become parallel to the asymptotic lines. And here minus 37, the mirror image of that one. So this angle is called angle of departure and can be determined by this relation.